So what we're going to try to do here, and I'll try to go quickly so as not to keep people, we are going to think about how we can best use both daytime and nighttime satellite imagery to measure local level economic livelihoods. And here we're going to be working in the sub-Saharan African context, where arguably good measurement is most needed. And let me thank many of the co-authors you can see down here at the bottom who have worked on parts of this over time. Okay, so two quick motivations on why to do this. So number one, this has been mentioned before, we depend typically on household surveys to make these measurements. Household surveys are absent or rare in many parts of the world. This map on the left from a review that we have sort of quantifies that in many countries, and this is really worse than sub-Saharan Africa. You have to wait decades or an infinite amount of time to get a nationally representative household survey. And even when these are done, they're often not geo-referenced in any way that's publicly available. And so it makes it very hard to use these data sources to do the sort of measurement and impact evaluation that we care about. Contrast this to the incredible amount of satellite information that is being collected over time. Nightlights is not on here, but as Chris gave a nice demonstration in the keynote, we're getting better and better at taking both high temporal and spatial resolution images of the Earth at night and also during the day. So this is daytime imagery, and here I'm calculating the revisit rate. So how long do you have to wait for a satellite to pass over and take a cloud-free image? So thanks to some recent launches, we're up at nearly an image per day. And you can compute the comparable survey revisit rate. How long would you have to wait for a surveyor to come to your house? And in sub-Saharan Africa, or even in the US, you're gonna wait thousands of years. Now, of course, we don't need to sample everyone. We can draw a random sample, a smaller sample, and get the nationally or regionally representative statistics that we want. So this is a little cute. But it's really to appreciate the fundamental difference in terms of the frequency of observation that we now get from satellites and from a range of different satellites. Okay, so what we want to understand, and again, this is in the African context, we want to understand, can satellites help fill in these large temporal and spatial gaps between when we have existing household surveys? And again, we're going to think of these household surveys as really useful as collecting a lot of rich, trustworthy data. And the problem really being is that we just don't have enough of them, right? So how do we help fill in the gaps? So as others have showed, we are going to adopt a pretty similar pipeline. So we are going to try to predict village level asset wealth in sub-Saharan Africa using two different types of imagery as input, nighttime lights imagery, and this is mainly going to be DMSP. We use a few years of VIIRS. Happy to talk more about how we do that. And because we're going back to the early 2000s, we're also using daytime satellite imagery with good spatial and temporal coverage. So here we're using Landsat, which is fairly coarse, 30-meter resolution, and but it's multispectral, right? It's not just the visible spectrum, it's higher spectra as well. Okay, and again, our labels or our outcomes are these village level wealth estimates that we have from the demographic and health surveys. In the data we use, these cover about 500,000 households and represent roughly 20,000 villages back about 2 decades in sub-Saharan Africa. Okay, so I'll spare you the details here, sort of the outcomes. I encourage you to blur your eyes a little bit here. But if we, the overall relationship between the model predictions and the ground observed measures, we explain about 70% of the village level asset wealth. And here we're actually pushing the models pretty hard. We are forcing the models to make predictions in countries where they have not been trained. So it's called cross-validation. So we'll train a model in Tanzania. We'll make a prediction in Kenya without it having seen any data in Kenya. And this is a rather hard test, and it's meant to mimic how you might use these models in settings where we don't have any data at all. So it's a hard test, and the model does pretty well. Again, we have R-squareds of 0.7, and these get higher, as you can see on the right, as we aggregate up to the district level. So there we explain 85% of the variation in district level asset wealth across sub-Saharan African countries. So to us, that looks pretty good. So what imagery is doing the work here. So we can then re-estimate these models. So what I just showed you was a convolutional neural network that combined both the daytime and the nighttime imagery. We can instead build one that only uses the nighttime imagery, only uses the daytime imagery. And what we find, at least when we're predicting in cross-section, predicting spatial differences, is that these two different sources of imagery do a little bit better when combined together, but both do reasonably well on their own. And they seem to be picking up very similar sources of information, as I'll show you on the next slide. One thing we've learned with the night lights is if you just estimate a linear model, linear and night lights, this actually does pretty badly. These need to interflexibly. There does seem to be some spatial information in the night lights. So training a CNN to predict the night lights does pretty well. And finally, we had this earlier paper where we had used transfer learning. We had initially trained a model to predict nighttime lights with the daytime imagery, and then taken those features to predict the final outcome. At least in this setting, transfer learning doesn't seem to help. It actually does worse than just using the night lights directly. So hopefully our earlier paper didn't put people off on the wrong foot here. Apologies. And again, this is just a correlation matrix between the predictions. And as you can see, these are, other than the linear, so scalar here just means linear, other than those, all the different imagery inputs are making pretty similar predictions once they've been fed through this convolutional neural network. So what we conclude from this is at least at this spatial scale for this outcome, these two different sources of imagery are giving us pretty similar estimates. That's in cross-section. We also want to predict changes over time. Our results here are going to be eerily close to what Gordon Hanson showed a couple hours ago. So now, not only do we want to predict spatial patterns, we want to predict temporal patterns. And here, because the DHS surveys, if you've worked with them, are not a panel in sub-Saharan Africa, we use a much smaller number of living standards measurement surveys, LSMS surveys in sub-Saharan Africa. We construct a village level panel and we try to predict it with the various types of imagery. Night lights is basically uncorrelated. Changes in night lights are basically uncorrelated with changes in asset wealth at the village level, at least in the villages that we observe. Daytime imagery are much better correlated. So again, we have R-squareds shockingly close to what Gordon showed between, so we explained about between about 35 and 50% of the variation in village level changes in asset wealth. But again, here, all of the power is coming from daytime images. We do not get any power from the nighttime light. So again, consistent with what Gordon showed. Okay, finally, just to wrap up, I want to think about then how we might use some of these derived estimates in downstream tasks. So particularly in thinking about doing impact evaluation, either in an experimental setting or in an observational setting, which we just, as we just saw some pretty nice examples of. And here, I think we really need to think carefully about what's baked into some of these estimates. So imagine two impact evaluation questions. Number one, what is the effect of electrification on wealth or some economic outcome? If you're using night lights, you might be pretty worried that you're going to find a mechanical relationship, right? Night lights is going to be in your outcome. Night lights is also basically your independent variable. So you would be pretty shocked if you did not see a relationship between those, but that relationship is going to be mechanical. So are you drawing the right inference? You might be worried in daytime imagery too. What's the effect of, let's say, road infrastructure on wealth? If you're using the daytime imagery, then it might be the case that the features that the daytime imagery are using to say a place is wealthy have something to do with road infrastructure, something that the machine can see in an image. And again, then you've generated a mechanical relationship between your independent and your dependent variable that might mess up inference. Finally, and this is, I think, is sort of a deeper problem that's a little hard to think about. So what if your treatment of interest, let's say some income transfer to keep it easy, actually changes the relationship between the image features you have and the outcome of interest? So here are a couple potentially silly examples. Let's say there's a tree planting intervention that generates wealth, but it also obscures light sources, right? So the treatment itself has changed your mapping of your input image to the outcome that you care about. Or, as has happened throughout the US and Europe, what if the wealthy towns take substantial measures to reduce light pollution, right? And this only happens once your town gets above some amount of wealth. Again, the treatment, getting richer here, has changed that fundamental relationship. So I think these are things we really need to think about when we use these derived estimates for downstream tasks. Okay, to wrap up quickly, so in our African setting, We find that daytime and nighttime images are largely complements when predicting in cross-section, but that the nighttime is not that useful, at least at a very local level, in predicting temporal changes. And then as I sort of suggested on my last slide, I think both have these sort of interpretability issues, these inference issues that are pretty important when we think about downstream tasks. That said, I think there are a lot of settings in which we're going to be less worried about these downstream tasks and where scaled estimates might be useful. So we have a startup, Atlas AI, that is using this machine learning pipeline that I mentioned and now generating scaled continent level asset wealth estimates across sub-Saharan Africa back in time to the early 2000s. And in about a month, we're going to have a public data release, a lot of these data. So come check out our website and get in touch if you'd like to work with some of these data. So I'll stop there. Thanks.